Hi students. Today I'd like to do a little demonstration for you. In front of you is an Omron absolute encoder. It's powered by 12 to 24 volts and there are 8 data lines coming out of it. These correspond to the bits of an 8-bit number. That means that as we turn the shaft, we can divide the circle into 256 discrete values. Those values are being read by an Arduino. So all of the 8 lines go over to port L, and I'm doing a direct port manipulation. If you're not familiar with that, direct port manipulation allows you to read 8 input pins all as one number. So the 8 values correspond to an 8-bit byte. And then we'll come back over. That's all going to Visual Basic to the output on the screen. So it's probably hard to see. We're going to jump into the computer in a minute. But as I turn the shaft, you can probably vaguely see that the numbers are changing. Okay, so let's jump into the computer and see what happens. It's warmer in here. So now that we're in the computer and we're happily next to the CPU where it's nice and warm, let's take a look at what happens as I turn the shaft on this encoder. So as you can see, I'm turning it, and I'm turning the shaft clockwise now. And the way I set this up is kind of unique. I have the input of the Arduino on pull-up resistors. That means that on each input line, there's 5 volts normally, and you affect the input by grounding it down to 0. That saves a lot of extra wiring. The downside of that is that I get an inverted input. Okay, but having an inverted input, namely, I should have 1, but I have 0. Again, I have 0, I should have 1. This is not a problem to deal with. We can flip all of these bits in one operation by doing a function called exclusive OR. Whenever I have a byte of information and I do an exclusive OR against that byte with all 1s, the bits all flip. So you'll notice I have my inverted input on port L right here. I do an exclusive OR, which is just a single line of code. And then magically, the bits all flip. So the 0 becomes 1, the 0 becomes 1, the 1 becomes 0, etc., 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 right down the line. Very convenient in a lot of functions. Okay, so in class, I told you that normally we have binary on absolute encoders. Well, I fibbed a little bit. Okay, yes, there are some binary absolute encoders, but they can lead to unstable readings. And the problem with a pure binary absolute encoder is that you can have multiple bits flipping at the same time. And that's a problem because you can get sporadic firings of an interrupt reader on a microprocessor. Again, this is getting into some pretty high stuff, but suffice it to say, you can have unstable readings if one pin in that byte fires before another one. So you can end up with double reads. The way we solve that is with gray code. Gray code is conceptually like binary. However, it only allows 1 bit to flip at any time. Unfortunately, we can't really count in binary. So what we need to do is have a gray code to binary conversion algorithm, which I've done in the background in Visual Basic. This binary number actually corresponds to the true position of the shaft. So my algorithm goes from gray to binary, and then binary to integer. So as I turn the shaft, the values linearly increase. And they're going to increase all the way up until I hit 255, and then they're going to roll over to 0. So 240, 250, and then 0. And if I keep on turning the shaft, it does the exact same thing. And I'm turning it a little bit quickly, and I have a slow sampling rate, which is why they're not going one value at a time. Okay, and I can go bidirectionally with this. So if I decide to turn counterclockwise, as I'm doing now, it counts down right to that 0 value. And we roll back up to 255, and we start counting down from 255 again. Okay? So this is how you make an absolute encoder go. I hope you found this interesting, and I'll talk to you later. Bye.